Hello, I'm Hyeong Park from Korea University. At this time, I will present the consistency learning via decoding path augmentation for transformers in human-object interaction detection. To briefly explain HOI detection, it is the task of localizing human and objects and classifying interactions between them. Existing HOI detectors commonly use a sequential approach that first localizes human and objects using an object detector and performs pairwise interaction classification using their features. However, the sequential detection requires high computation cost. So in order to overcome slow inference time, there have been attempts to perform object detection and interaction classification in parallel way. Here, an additional auxiliary subset predictions such as human interactiveness or object interactiveness are used during training and post-processing to compensate for the falling accuracy of the parallel structure. Recently, HOI detection using a transformer-based architecture has been proposed. HOI transformers achieve state-of-the-art performance and fast inference speed by directly predicting the HOI element at once. Motivated by those various inference passes of existing HOI detectors, we propose cross-path consistency, which utilizes various inference passes to apply simple consistency regularization to transformer-based architectures without additional data and inference time. Cross-path consistency shares the key concept of cross-task consistency, called inference path invariance. Both schemes utilize other tasks to train main target function fxy, which is used in test time. However, cross-task consistency requires a pre-trained network of auxiliary tasks, while our cross-path consistency can be done from scratch since the main task is divided into multiple subtasks. HOI transformers have a common form of adding an interaction classification head to DTR with an ImageNet pre-trained network, followed by an encoder-decoder structure. We assume that this structure has inference paths of image X to HOI, which we will use for test time. For diverse inference passes, we augment the decoding paths, which do not immediately extract all HOI elements with a single decoding stage, but use different combinations of subset predictions to create multi-stage inference passes. For example, in the case of pass 2, the first decoding stage performs prediction on human and object. Then, output embedding the first decoding stage fed into the next decoding stage. In the second decoding stage, the remaining HOI element interaction is predicted. By creating diverse inference passes, we add a regularization loss term that maintains consistency between the predictions obtained by each pass. We apply two components to cross-path consistency. One for sharing the parameters of all decoding stages in perspective of knowledge sharing, and the other is using different position embeddings for each decoding stage. To specify which pairs of query output to be consistent, we present cross-matching, a simple method that pairs predictions from each pass with its corresponding ground truth label. The output of query matched with the same label are paired to compute consistency loss. For the experiment, two famous HOI benchmark datasets were used, and our training scheme showed significant performance improvement when applied to the vanilla HOI transformers in both datasets. In summary, cross-path consistency learning enforces the predictions from various inference passes to be consistent, which results to having better generalization ability without increasing model capacity. Although we demonstrated our work on HOI detection, we believe that our framework is applicable in various tasks or non-transformer architectures. Thank you for watching the presentation.